Jnanam paramam dhyayam. Knowledge is supreme.
And now we want to prove another one, namely saying that every element has got a unique representation is equivalent to saying that the set B generates, that is the linear span is V, and if a linear combination is 0, if a linear combination is 0, then all the scalars must be 0. That is what essentially we did in the previous thing also, right. So, from 2 to 3, right, is that obvious? 2 implies 3, because if we assume every element has got a unique representation, and if there is such a representation that sigma alpha I beta I is equal to V I equal to 0, the right hand side 0 is equal to 0 into V I summation. So, what will uniqueness say? Uniqueness will say that each alpha I must be equal to 0. So, what I am saying is 2 implies 3 is obvious. Is that obvious to everybody? Yes, because if a linear combination is 0 and if this representation has to be unique, then each alpha I has to be 0, and that is what 3 is saying, is another way of saying, right. So, 2 implies 3. Let us see why does 3 imply 2. So, that is again obvious. So, let us look at 3 implies 2. So, let sigma alpha I V I be equal to 0, I equal to 1 to n. So, that is 3, right. So, let imply alpha I equal to 0 for every I. So, this is given to me, this part is given, that is a statement 3, right. To show 2, what I have to show? Every element has got unique representation. So, let V belonging to V be such that V is also equal to sigma alpha I V I, also equal to sigma I equal to 1 to n beta I V I. Suppose there are 2 different representations. Once again this will imply sigma of alpha I minus beta I V I is equal to 0, right. Take everything on one side, that is equal to 0, and what does that imply? 0 has got a representation by uniqueness for 0, this implies alpha I is equal to beta I for every I, right. So, that way both are obvious from each other. So, statement 3 is equivalent to 2 is equivalent to 3. Let us look at final one, which says B is a minimal set. No, sorry, this is a wrong thing, it should be maximal. So, let me correct what is the correct statement of 4. So, this is a typo there. So, 4 says B is a maximal, instead of word minimal it should have been maximal subset of V such that 0 belonging to V has unique representation. That should be statement 3. So, let us prove that. So, I want to prove that 3 equivalent to 4. Okay. So, assume 3. So, what does 3 say? That the linear span, so that is linear span of B is equal to V, and sigma alpha I V I equal to 0 should imply alpha I equal to 0 for every I. So, that is what is given to me, right. What is to be shown? B is maximal with this property, right. with this property star. 0 has got unique representation, right. Suppose not, suppose it is not, right. That means what? That means there exists something one more which I can add to it, right. So, there exists a V belonging to V minus B such that if I look at S1 which is equal to okay, B1 or S1 which is B union this V, right. So, look at this V has, so if not it is not maximal with that has property star. If it is not maximal with some property, that means I can add one more, make it bigger with that property, right. So, I am adding a vector V which is not in B to it. Now, look at V, V belongs to V, and what is V? What is given to me? L of B is, right. So, this is L linear span of B. So, implies what? V is a linear combination of for some alpha I, right. But what does that mean? That means again take everything on one side. So, V minus sigma alpha I V I is equal to 0, right. So, here is 1 multiplied by V plus something that is equal to 0. That means what? 0 does not have unique representation, right. So, this property star is contradicted. We said this should have the property, but we have written a linear combination equal to 0 where not all coefficients are 0. So, not possible. So, hence 4 holds, right. So, this is a proof that 3 implies 4. Let us prove the other way around. So, finally, we want to prove 4 implies 3. Okay. So, what is 4? 4 says B is minimal, right, B is maximal such that sigma alpha I V I 1 to n equal to 0 implies alpha I equal to 0. So, that is what is 4. And what we have to show? We have to, right, to show 3. So, what is, it already has that property. So, what is to be shown to prove 3? Say in 3 we want to show that there are two things, one it spans, right, and secondly it has that property unique representation, right. So, already unique representation is already there given by 4. So, what is left to be shown? To show that is L linear span of B is equal to V, that is what is to be shown, right. So, let us take a vector V. Okay. If not, if it is not true, what will happen? If L of linear span of B is not whole of V, that means there is a vector outside it, right. So, if not, there exists a vector V belonging to V minus linear span of B, right. Now, consider this vector V. Now, consider this vector V. Okay. So, there is a vector V which is outside the linear span. Okay. Now, we want to show that if not there is a vector V. So, let us consider the set B. Okay. See, till now we have not used it is maximal, right. So, now let us consider B union V. Okay. And look at the linear span of this thing. That will mean what? that means 0 should be equal to 0 is inside this, should be equal to some alpha times v plus, right, 0 belongs to this linear span always. So, 0 should be a linear combination of elements in B and V. So, alpha times V plus some alpha j V j, j equal to 1 to n for some alpha alpha j. Is that okay? Now, can alpha be 0? If alpha is 0, then what will happen? Sigma alpha j V j is 0 by the given property, right. What is the property 3? This says for 4 it says sigma alpha I V I equal to 0 should imply each alpha I is equal to 0. So, if alpha is 0, then alpha, can alpha be 0? No, because alpha equal to 0 will imply alpha j equal to 0 for every j also by given hypothesis, right. So, if alpha is not 0, then what does this equation tell me? What does this equation tell me? It says I can write V as minus 1 over alpha summation alpha j V j, right. And what does that mean? V is a linear combination, right. So, V belongs to L of linear span of B, right. So, V belong, any element outside also is a linear span. That means what? That means there no such V exists. That means V is equal to linear span of B, right. So, implies that linear span of B is equal to V. Okay. Okay. So, that basically means, let me go through the statement once again. It says you are given a vector space and you are given a finite set, right. We want to know when is a finite set a basis. One is, it is a basis means it is a minimal set of generators, right. Second, every element in the vector space has a unique representation in terms of elements of V. That means, every element V in V is a unique linear combination, those scalars alpha i's are unique. And the third says every element is a linear combination and 0 has unique representation. So, this says 0 has unique representation. So, we are saying that every element has unique representation is equivalent to saying that 0 has unique representation. And in terms of the maximality and minimality, it says B is maximal subset, right, such that 0 has unique representation, right. So, these are 4 equivalent ways of describing what is called a basis. All will be useful in constructing basis for vector spaces. So, we will see that how these are useful.